Good afternoon, everyone. Welcome to our Friday afternoon robotics seminar, RI seminar. Today, it's my great pleasure to introduce Dr. Noémie Jaquier from KIT, Karlsruhe Institute of Technology in Germany. I'm trying to get your bio. There's many things. Dr. Jaquier did her bachelor's degree at EPFL in microengineering, master's degree at EPFL in robotics and intelligent systems. Okay, plus another minor in neuroscience, correct?
Computational neuroscience.
Okay, computational neuroscience, indeed. Okay, excellent. And then also her PhD in affiliation with EPFL, but also at, I'm going to mispronounce, IDIAP, EDIAP Research Institute, in collaboration with EPFL, and is now with Tamin Asfor at KIT, and also currently a visiting postdoctoral scholar at Stanford, working with Osama Khatib. I think you might know Tamin and also Osama. And so without further ado, she's going to tell us wonderful things. Oh, I will say one other thing. Fantastic workshop, IROS 2022, on geometric methods. We were all, I think you're seeing hands in the crowd saying, yeah, woo! It was standing room only. It was a fantastic workshop. I learned a ton. And so it's a great pleasure to have you here to tell us more. Whenever you're ready, take it away. Thanks.
Thank you. Thank you, John, for the kind introduction, and thank you for having me here. It's great to finally visit Toronto. And as you mentioned, the IROS 22 tutorial, there will be the follow-up iPad and Manifold, so please come. Okay, today I would like to talk to you about, from data structure, physics, and human knowledge, a manifold of robotics geometry. So robotic manipulation involves complex skills, which can be learned by robots in different manners. One popular approach is learning from demonstration, in which some demonstrations that involve the important features of the task are provided to a robot. So we have here a screwing example, and in this example, for instance, we need to have the pose of the robot needs to be precise, and the robot needs to be stiff or compliant in different directions. In addition, we would like our robot to be able to cope with uncertainty and to adapt to new situations. To do so, we may use trial and error-based approaches, as well as interactions with humans. In addition, our robot is a real system. It evolves in the real world, so we would like it to be able to learn in real time. That entails that we would like to be able to learn from few demonstration, to have data-efficient skill learning and adaptation strategies, or to adapt fast with few interactions with the human. As you may have seen, some skill parameters may actually not belong to a Euclidean space. So for instance, the orientation of the end effector here is often represented as unit quaternions, which have a unit norm, so they belong to a sphere. And in this example, again, stiffness ellipsoids are positive definite matrices. That means that they have only positive definite eigenvalues. In other words, the skill parameters has a specific intrinsic geometry, which we may leverage as inductive bias to guide learning algorithm and to improve their efficiency. So in this talk, I would like to show you how we can introduce inductive bias in the form of geometry into learning and control algorithm. So in the first part of the talk, I will show you how we can leverage inductive bias in the form of a data structure. So this is related to the example I introduced you in the previous slide. And this may be the most common way to actually see inductive bias in the form of geometry. In this talk, I would like to take a slightly wider view on this, and I would like to show you how we can also consider geometry that comes from physics and from human knowledge. So in the second part of the talk, I will show you how geometry naturally arises from robot dynamics and how it can be used to analyze human motion and to then transfer them to robots in an energy efficient manner. Finally, in the last part of the talk, I will show you how we can introduce geometry in the form of human knowledge as inductive bias. And here I will see human knowledge that are coming from robotic taxonomies and show you how we can form latent spaces that include the knowledge from those taxonomies. So let me jump in the first topic. So as I told you, relevant robotics parameters feature a variety of geometries. So examples include the Euclidean space. So I guess all of you know this space. We encode position, we encode forces in that space. Other example that I already mentioned is the sphere, in which we represent orientation and any type of directional data which have unit norm. Another example is the manifold of symmetric positive definite matrices, in which we represent control gains, inertia matrices, manipulability ellipsoids, any type of covariance in general. Another example is the torus, where we can represent joint configuration and any type of periodic function. And finally, as a last example, there are many more, but as a last example here the special orthogonal group, which we also use to represent orientation, and this is actually a building block for other types of data structure. So what we would like to do is to design a learning algorithm that account for all these different geometries. So basically the mathematical space that I showed in the previous slides having in common that all of them are what we call Riemannian manifolds. So I will give you here a very brief introduction on Riemannian geometry, just so that everybody is now on the same page. So very intuitively, a Riemannian manifold is a mathematical space that is curved, but locally it looks Euclidean. A little bit more formally, that means that for any neighborhood on the manifold, you can define a homeomorphism, that is a one-to-one invertible mapping between your neighborhood and a subspace of the Euclidean space. Once you can do that, you can actually use this to define at every point on the manifold the notion of tangent space, which is literally a space that is tangent at your point, and the space is Euclidean. So this is what defines a smooth manifold. Now we have a manifold that is Riemannian at the moment where we endow it with a so-called Riemannian metric, that is an inner product that is defined on every tangent space on the manifold. So this inner product is defined based on the Riemannian metric that you can see here, which is a symmetric positive definite matrix which varies smoothly through the manifold. What is cool is that once we actually know this metric, we know the entire intrinsic geometry of our manifold. So this fully characterizes the geometry of our space. This allows us to define the notion of norm of a vector on the tangent space, as well as the notion of length and distances on the manifold. It also allows us to define the notion of geodesic, that is minimum energy, minimum length curves. Intuitively, you can see them as the generalization of straight lines, but to those curved spaces. These notions allow us to define some maps, which are very useful and that I kind of use in all the algorithms that I will present after, which are called the logarithmic and exponential map. So the logarithmic map a point on the manifold onto a vector on a tangent space. What is cool is that once you are in this tangent space, you are in a Euclidean space, so you can apply all the usual operation on this vector. And once you apply the operation that you needed to apply, you can map it back onto the manifold, so from the tangent space to the manifold using this time the exponential map. A last operation that is useful is the parallel transport, which allows you to move vector from one tangent space to another. So you have to be mindful here that when you have a tangent vector, it belongs to a specific tangent space, and you cannot just treat it as if it was just a vector anywhere in the space. It really belongs to that space. So if you want to compare it with a vector in another space, you actually have to move this vector to this other space. And this is what parallel transport does. Okay, so this is for a small introduction. Now what I would like to show you is an example of algorithm which benefits from inductive bias in the form of geometry coming from data structure. So in the introduction, I mentioned that I would like to achieve data-efficient skill learning and adaptation, and one algorithm that is well suited to do that in robotics is Bayesian optimization. So let me briefly introduce Bayesian optimization so that, again, everybody is on the same page. So Bayesian optimization aims at minimizing an objective function which is considered as a black box. That is, we don't have any closed form solution for this function f that you can see here, but we can observe this function at any point of our parameter space. So we can here, for any point of the parameter space, we can observe the value of this function. So you might here in red some observation. So what BO does is that it first models the objective function. So this is typically done with the Gaussian process. So we put a Gaussian prior on the function, and then by computing the posterior with respect to the observation, we find a model of the function that is represented by the mean of the Gaussian process. And the GP also gives us a notion of uncertainty. So you can see here this uncertainty in the form of the envelope. So intuitively tells you where you actually had observations or not. Once we have this model, what we do in the second step is that we build a so-called acquisition function. So this acquisition function is a trade-off between exploration and exploitation. Exploration because we are going to try to query the points in which the model is telling us your function is minimum at that point. And exploration because we also want to explore the part of the space where we don't have much information, so the part where we have a high uncertainty. So we define this acquisition function based on our model on our Gaussian process. Then we maximize it, and the point in which this acquisition function is maximized is the point that we are going to query next. So we repeat this process, and usually Bayesian optimization in few iterations finds an optimum. So this is the classical BO. What we would like to do now is to actually use this algorithm to be able to optimize for data that are on a specific manifold. So when we want to do that, we have to do two modifications in the algorithm. The first one takes into account the fact that the quotient process is completely specified by the mean and by the covariance, that is the kernel function. So in the classical Euclidean space, the kernel is usually defined as a function of the Euclidean distance. However, when you have data on the manifold, the Euclidean distance is completely meaningless. So imagine on the Earth, you don't want to measure distance between A and B through the Earth, but actually on the surface of it. So what we propose to do is to actually use Riemannian formulation, which intuitively account for the distance on the manifold instead of the distance in the Euclidean space. I will give you a little bit more detail on how we do that just after. The second modification concerns the acquisition function. So here we account for the fact that the quality of the next query point depends on the optimization of this acquisition function. So again, in Euclidean space, we simply optimize over a subset of this Euclidean space. But then when you have some constraints, you can usually we do that by constraint optimization. When your data lie on a manifold, this is not the most efficient approach. Instead, what we do is that we use a Riemannian formulation, which allows you to directly optimize on the manifold in an unconstrained manner. Okay, so let me go a little bit deeper into how we actually generalize, in this case, squared exponential kernels, so the kernel that I had in the previous slide, to Riemannian manifolds. So to do so, we have to go back to the root of what the squared exponential kernel actually is. So the square exponential kernel is actually defined as the covariance of a random process f, and this random process satisfies the stochastic partial differential equation. This stochastic partial differential equation depends on the white noise, and it is defined as a function of the Laplacian of our random process. So the idea is that you solve this partial differential equation, you obtain an equation for f, you compute the covariance of this random process that you obtain, and this gives you your kernel. Now when we want to actually formulate the kernel on Riemannian manifolds, what we have to do is to adapt the stochastic partial differential equation to the Riemannian case. So here, instead of using white noise, we use white noise with respect to the Riemannian metric. So remember, this Riemannian metric is what gives you the entire intrinsic geometry of your manifold. So we use that to define the white noise. And then instead of using the Laplacian, we use the Laplace Beltrami operator, which is actually a generalization of the Laplacian to Riemannian manifolds. And then the process is the same. We solve this equation for f, we compute the covariance of f, and this is the type of kernel that we obtain. And you see that this kernel actually depends on the so-called Laplace Beltrami eigenvalues and eigenfunctions, and it is a sum of the multiplication of those eigenvalues and eigenfunction, very similar to actually what the Mercer theorem tells us that Euclidean kernels should look like. So to give you an example, here is the kernel that you obtain when you do this for the circle. So what you can see is that we have here, again, an infinite sum over the space of real numbers. No, I don't know anymore the name of this one, but basically 0, 1, 2, 3, 4, 5. Integers, yeah. Sorry for that. Okay, so we have a sum over the integers. And what you see is that basically the small term that you have here in blue is a way to measure all the distance of all the possible paths between the 2 points that you are considering on the circle. So when n is equal to 0, you measure the shortest path between those 2 points. When n is equal to 1, you do a full tour plus a little bit. And when n is equal to -1, you go the opposite way and you actually measure the other side distance. So you take all those possible paths, and basically then they are summed in this kernel. So that's the idea. Okay. Now the second part that I told you we're modifying is the optimization of the acquisition function. So here, instead of using Euclidean constraint, Euclidean methods, we use optimization methods on Riemannian manifolds. So I will give you here the example of the conjugate gradient descent on Riemannian manifolds, but in principle you can use other algorithms that are maybe more complicated. So what we want to do is to maximize the acquisition function, which is equivalent to minimizing minus the acquisition function. So the conjugate gradient descent on Riemannian manifold starts with an iterate, which is somewhere on the manifold, and the search direction. The search direction here is defined on the tangent space of your iterate. Okay? So the first step is that we want to find the next iterate. So for that, we actually solve a line search problem, which is going to tell us at the end of the day how far in the search direction we are going. So we solve this line search problem, and then we find basically this scalar alpha, which scales the search direction. And we use the exponential map to map from the search direction in the tangent space onto the manifold. And this gives us our next iterate. Once we have the next iterate, we would like to find the next search direction. So this is where we are actually using Fourier transport. So we want to take the old search direction and to move it to the tangent space of the new iterate. Then we compute the gradient of our function. So the gradient is also a term that lies on the tangent space of our current iterate. And once we have those two terms, we actually sum them as a weighted sum, roughly speaking. And we iterate those two steps until we actually converge, and then we set the point that we're going to query as the optimum that we find while maximizing the satisfaction function. So let me show you a little bit how that actually works in a toy example. So here we want to optimize the Atlee function on the sphere. So you have here the ground truth of the function and the ground truth onto the projection. So you see you have here x1, x2, x3, and then you recover x1, x2. The vertical axis is the function, and here x2, x3, and the vertical axis is the function. The minimum of the function is here indicated by the star, and this is the point that we are aiming at finding. So I will show you how the Gaussian process model mean evolve on the sphere, and how the Gaussian process mean and its covariance evolve on the projection. So you see here we have the mean in purple, and the envelope that is gray is actually the covariance of the Gaussian process. And I will show you the current best as a function of the equations. So now the Gaussian process, the BO starts, and you see that at the beginning it exploits a lot, and very quickly we reach something that is very close to the optimum. And what it does after is more like an exploration phase, where basically it explores the areas that are uncertain, and you see that in the projection the uncertainty gets reduced. And after like 40-50 iterations, we actually have a very good model of our function, and we have an optimum that is very close to the ground truth minimum. This is an example of convergence graph that we obtained for this Bayesian optimization. So you see here, those two curves in blue and orange are the Riemannian approach with different kernels. This one in purple is an approximation of the Riemannian approach, and those two are the Euclidean approaches where we don't consider at all the geometry of the manifold. So the goal here is to, of course, find the minimum, so to go as low as possible, as fast as possible. And you see that basically by considering the geometry, we have faster convergence, we obtain a better accuracy, and we actually allow resolution. Okay, let me show you how this actually works in a real robot. So here we have our Armor 6 robot at KIT in the kitchen, which aims at opening the dishwasher. And what we want to do here is to optimize the orientation of the wrist in a very simple policy. So the policy here is that we set an orientation, then we approach the dishwasher. When we make contact, we slide up until we actually reach the door handle. So we want to find the optimum orientation such that at the end of the day, we actually reach the door handle. We want to not have too high external forces, so we want to have a measured contact somehow with the dishwasher. Otherwise, we just plainly break the fingers. We actually did that several times, so we really want to avoid this. And we want to have a high volume force manipulability at the end to actually be able to apply the force to finally open the dishwasher. So here are some runs on the robot. So this is the initialization. We give a random orientation, and you see that we have too high forces, so we don't reach the door handle. Then the BO starts. We actually have here 15 runs in total. So you see that here we had high external forces because the pinky finger actually stayed a bit stuck. So this is typically what happens when you break the fingers. This is a better run, so we see that the BO is slowly going towards something that is more optimum. And you will see, after this one, you will see the final results of the BO optimization. And you see that basically we have here external forces that are manageable. We reach the door handle, and at the end we have enough force to actually open the dishwasher. So what I wanted to show you here is that when we consider geometry from data structure as inductive bias, we're able to reach faster convergence, better accuracy, lower resolution variance, and we actually have models that mathematically are correct. So this is the end of the first part of the talk. Maybe that's a good time to take a couple of questions, and then I will switch to the second part.
Questions?
I think
Go ahead.
it's more like an understanding question. So in this example that you're giving, it's the unknown are basically kind of some physical parameters of your, like, because you said like you deal with problems where the cost is unknown, but you have a pretty good parametric form of your cost here. But I guess the unknowns are like some parameters in your cost. Did I understand?
Exactly. So the unknown is this joint, this orientation Q, and the point is that you cannot really differentiate that cost with respect to the orientation Q, or you don't have a direct mapping between Q and that cost. So you can make a run and observe the value of the cost at the end of the day, but you cannot like predict in advance, given this orientation, this will be my cost.
Because you don't know how these depend on
Exactly.
Q actually. Yeah, now I see that Q doesn't appear.
Exactly.
Okay, makes sense. Thanks.
Other questions? Yeah.
This is just a general question on optimization on manifolds, but if you know something about the objective function, like it's convex on the manifold, do you still need to do this like iterated search, or are there techniques where you could go straight to the global minimum?
So generally when you have optimization on manifolds, you don't have, it's very rare that you have closed form solution. Maybe you just don't have even closed form solution. So even for, let's say, a typical least square problem, where in Euclidean space you have a very clear solution, we know it, you can just write it down, compute it. In the remaining case, you still need to go through an iterative process.
Thank you.
Could it be totally different approach to be taken for the case of discontinuity, so which definitely is not a Riemannian manifold?
Can you maybe repeat with the mic? Sorry.
My curiosity is that, so should we like use another approach for the cases that we have discontinuities, not necessarily Riemannian manifold?
Yeah, so if your search space is not Riemannian, then you may need to change your approach. Yeah. So you have to
Do you have
again
any
define.
insights on which approach might be applicable there?
That's a good question. So either you have to define. So I mean, the simple thing that you can do is to try to go Euclidean and see what happens. If you don't have any other solution, you could try to put a metric on your space and then to still try to define the Riemannian space and then use the approaches. Then I think it depends a lot on your problem, what your problem is looking like, and what you can actually use in your specific problem. I would say.
Sorry, my question ties into what you just answered. If you don't know what your Riemannian metric is, can you learn that from data as well?
Yes, you can. So typically what is made now in the literature or nowadays is approaches where you build a latent variable model from your observation, and the metric is going to come through this latent mapping. So, and then you have actually a Riemannian metric in your latent space. Yeah. Okay, thanks. Okay, let me go to the second part of the talk. So humans are naturally able to generate skillful motion. In particular, they are able to generate optimal trajectories despite the high redundancy and high dimensionality of their configuration space. So our robots are actually getting high dimensional as well. Their configuration space is getting high dimensional, especially for humanoids and also in some cases for exoskeletons. So for all these robots, there is a need to actually produce reliable, dexterous, and energy-efficient motion, despite the redundancy and the high dimensionality of their configuration space. So what we would like to do here is to take into account the geometry that comes from their dynamics, as I will explain later. And this is a case of inductive bias that comes from the physics of the problem. So to deal with this redundancy, what roboticists have done is to borrow the concept of synergies from neuroscience. So synergies are a coherent cultivation of motor signals and then allow you to produce motion that are synchronous. However, synergies have often been extracted using linear methods, such as principal component analysis, and these completely disregard the nonlinear characteristics of the robot configuration space. A bit later, synergies have been extracted using latent variable models, which are nonlinear, but they still don't account for the dynamics of your problem, so they are still physically meaningless. So what we would like to do is to be able to extract synergies that actually account for the robot dynamics. So what we do here is that we see the space of joint configuration as a Riemann manifold. So remember that a Riemann manifold is completely specified by the Riemann metric. And in that case, what we do is that we say that we have a Riemann manifold made of the set of joint angles, and the metric of that space is equal to the mass inertia matrix of the system. What it gives you is that you have the configuration space manifold, that is, in this manifold, trajectories are simply trajectories of joint angles. What is interesting now to have a look at is the shape of the geodesics in this space. So remember, the geodesics are this generalization of straight line to that space. They are the shortest path, or the minimum energy path between 2 points on the manifold. So if you take the equation of geodesic, this is what it gives you, and you will see that by explaining a little bit those terms, you will directly recognize this equation. So the first term gives you the mass inertia matrix times the joint acceleration, and the second term actually just the influence of coordinate forces. That is, you actually recover the classical dynamic equation of motion with 0 external forces at work. At the end of the day, what that means is that the geodesic in the configuration space manifold correspond to passive and to minimum energy trajectories of your system, of the robot. So the configuration space of a human can also be viewed as a mechanical system, so we can also see the configuration space of a human as a Riemann manifold. So one particular hypothesis when you study human movement generation is that human movement follow minimally forward path. Now we can see that from a geometric perspective, and that would just mean that human movement follow geodesics in the configuration space manifold. This hypothesis has been checked in the literature for 4 degrees of freedom arm here by Wies and colleagues, and extended theoretically to the entire body via the geodesic synergy hypothesis. So here we wanted to bring this hypothesis one step further, and we hypothesized that complex human movements can be modeled not only as geodesics, but as sequences of geodesics, or sequences of geodesic synergies. So to verify this hypothesis, we took recorded human motion, and we performed 2 steps. So in the first step, we actually segmented the motion that was given into different geodesics. So to do that, we actually have a look at the velocity along the trajectory, and we always compare the current velocity to the initial velocity that is spiral transported to our current location. So intuitively, we compare the current with the initial velocity. If they are aligned, it means that we are still on the same geodesic. If they differ by a given angle, it means that we are changing geodesic, and this is where we put a new synergy, so a segmentation point. Once we have the segmented motion, we would like to see if the segments actually do correspond to geodesic. So we reconstruct the geodesic between any start and end points of each segment, and we check if it matches the measured human motion, so the ground truth. So here is an example of motion that we considered. So here is a motion of the right arm. It's a pointing motion where we point successfully up, middle, and down. And I will show you the reconstruction using the Riemannian approach, which I just showed, and the Euclidean approach, in which you do the same thing, but you just consider that the configuration space is actually Euclidean. So here is the reconstructed motion. So it's a bit hard to see, but you can check that the elbow trajectory is actually quite different. And then when you have a look at the hand trajectory, so what is plotted here in colors, you see that clearly there is a big difference. Now comparing that with the ground truth, so we see here, this is 2 dimensions of the hand trajectory over time. In black, we have the ground truth, so the measured human motion. In red, we have the results of the Riemannian approach, and in blue, the results of the Euclidean approach. And as you can see, the Riemannian approach actually perfectly reconstructs the measured hand trajectory, while the Euclidean approach, for example here, significantly differs. Now we can have a look at the joint angles. So here is only 3 of the 7 joint angles that we consider for the human arm, 1 for the shoulder, the elbow, and 1 for the wrist. Again, in black you have the ground truth, and you see that basically the Riemannian reconstruction completely matches the ground truth, while the Euclidean is quite different in some cases. So this means that the Riemannian model successfully predicts hands and joint trajectories, and that we verify that we can actually model human motion as sequences of geodesics. So now that we showed that, we would like to be able to exploit similar principle to actually generate energy-efficient motions of robots. So what we wanted to have a look at here is how can we actually transfer motions that are generated by humans onto robots, such that the main characteristics of the motion are conserved, but that the generated trajectory actually is optimal or energy optimal for the robot at hand. So we proposed a very simple framework where we first get a human motion, we segment it into several geodesic synergies, then we map the start and the end point of each segment from the human workspace to the robot workspace, and then we link each start and end point with the geodesic in the robot configuration manifold. So here is again the same motion as measured in the human, and here is the transfer that we obtain on our Armor 6 robot. So here you can notice that the Armor 6 has 1 more degrees of freedom, so it's a very different, and that dynamically it's very different from the human. And you see that the motion is clearly recognizable, so we maintain the main characteristics of the motion, but it is now optimal energy efficient for the robot. So basically we are able with that to generate optimal energy minimizing motion that account for the robot dynamics. Now there are some cases where in your configuration space you may have a region through which you don't want to go. So this is typically the case because we have joint limits, and then you don't want the robot to self-collide or to collide with an obstacle. So we would like to be able to actually account for those no-go regions and avoid them while still being able to generate energy efficient motion. So for that we propose to modify the remaining metric such that we basically produce acceleration that brings us away from no-go region. So to do that we used barrier functions, and here you see, so in blue we have the direction to the no-go region. In black it's different velocity, you can see them as a joint velocity. And in red, this is the acceleration that is produced by the additional metric. So it pushes always away from the no-go region. We can use the same techniques to actually pushes us away from no-go region in task space. So we just pull back basically the direction to the obstacle in task space onto joint space, and then we have the same modification of the metric. So here is an example. This is a geodesic motion that is produced again on the Armor 6 robot. You see that here the motion is going relatively straight up. And then we add a table, and basically we modify our metric to add an additional term for joint limits, for self-collision avoidance, and one for the obstacle avoidance. And this is the new motion that we obtain. So we see that the robot actually now perfectly avoids the obstacle. Another example, we have here a human motion, which again we want to transfer to our robot. So here is the transfer motion, and you see that here I'm trying to keep that board actually fixed in space, and this is in the middle of the trajectory of the robot, so the robot is actually pushing me. Then we add those terms for collision avoidance, and you see that now I don't need to move the board anymore, the robot is avoiding it. And what is quite nice here is that it avoids it not only by going strictly below or strictly in front, but it's like a combination between the two. So it's like the motion that is the most energy efficient, but that still avoids the obstacle. So this allows us to generate optimal energy minimizing and collision-free motions that account for the robot dynamics. So in summary, by taking inductive bias that comes from the geometry that we obtain from physics, we are able to simply generate dynamic motion of the system to have energy minimizing trajectories that are specific for the robot at hand. So I will be again happy to take some few questions now.
Questions?
Thanks for the talk. I was wondering how precise do your, for this part in particular, how precise does the actual dynamic model of the robot need to be to take advantage of this kind of optimization?
So it doesn't need to be completely exact. Of course, the more exact you are, the closer you will be to being completely energy optimal. But I think you can have exactly the same model that you usually use when you have dynamic control, basically. So you don't need anything more precise. If you have a rough model of your dynamic, you can already use that.
I was wondering, for when you add these terms for joint limits and obstacle avoidance and that sort of thing, what am I losing or giving up by doing that? Are there any mathematical properties that I no longer get, or are things slower, computationally more challenging? Is it like, yeah, what is the trade-off I'm dealing with?
Mm-hmm. So there are a couple of disadvantages that arise when you add those terms. So one of them is that it's true, you have more terms to compute, so of course, computationally you're a little bit less efficient. Not by too much, generally depends how you are able to actually compute this direction. So this is where the computational cost comes from. Another issue is that sometimes when you have the mass inertia metric, your space is geodesically complete. So you can always go from one point to another with the geodesic. When we add those metrics, you may lose this. So it happens sometimes that you don't have a geodesically complete space. Just for your information, so there is a paper that actually went out a couple of weeks ago, I think, on Archive, which is exactly improving that and making the space geodesically complete. So that can actually be solved.
Can I ask one?
Sure.
So, adding these extra terms for these obstacles, it sounds like somewhat reminiscent of like potential field kind of methods.
Yeah.
Is there a connection there? And if there is, do I need to worry about local minima with this approach?
Yeah. So there is definitely a connection. You can actually see that as adding external forces to your dynamic equation of motion if you want. Then you can worry about local minima if your space is not geodesically complete, because then you may reach something weird. I think at the point where your space is well defined, you should be good. In our experiments, we never had really issues with that. Then, I mean, we didn't push the approach too far either. I mean, we tested it. This is the type of examples we did. Maybe now if we start really adding 10 obstacles, that may become more complicated.
Yeah, it's not a super cluttered
Yeah, exactly.
environment. Yeah.
So we have to test that actually.
Thanks.
Thanks, this is really kind of blowing my mind, this talk. But I was wondering if you had to estimate the human's mass matrix in order to do the mapping of the geodesics.
Mm-hmm. Yeah, so we do need an estimate of the human mass inertia matrix. Fortunately, we actually have a human model in the lab which has kinematics and dynamics, so we just took it and we use it. So it's a model that was made by, it's a paper from Liva and all of 20 years ago. I think. Those are the dynamics part we have there.
Okay, so if you have any two, I guess like robots or a human and a robot where you know their mass matrices completely, then you can essentially map any geodesics from, or any motions really from one to the other.
Yes.
Thanks.
Yeah, at the beginning you showed a ballerina. Sorry, you showed a ballerina bouncing on a beam. And I can imagine there's like a in-flight phase and a phase where you're on the beam. And maybe those problems have different geometries. And so can you plan between those different phases using these methods?
So in principle you can, yes. You have, because at the end of the day you have joint configurations and you're going from one to the next, right? The thing that you probably have to take into account here that we don't have in this formulation is the fact that we are acting in the presence of contacts. So then is the question how your contacts, if and how they're modifying the geometry of your space. So this is something we actually were investigating now.
Right, so if I understand correctly, you're targeting optimal motion from humans into optimal motion of robots, even though there is a degree of freedom difference, right?
Yes.
So the transformation between these two spaces does not have to be a different morphism. It can be some sort of projection.
So if you really want to go from one space to another, you need some kind of diffeomorphism. Here what we basically do is that we have those segments and we transform them from the workspace of the human to the workspace of the robot, which is Euclidean to Euclidean, right? And then we just link each start and end points in the corresponding manifolds.
So does that say anything about having to plan in a space that's difficult and first planning in a space that is easy and then transforming that back into a space that is difficult?
No, that wouldn't help us for that. Because at the end of the day, once you have the start and the end points of each segment, you still need to construct a geodesic between the two. So if the geodesic is hard to get in that space, it's still hard to get in that space. But yeah, then we could think about alternative approaches where you really have mapping from a manifold to another, and the mapping is easier to get than the geodesic in the complicated space. But that would be like a slightly different approach.
Thank you.
the last one, and then I move to the third part.
This means no one can ask questions at the end.
Thanks. It's related, so hopefully we'll be quick. So, sorry, I was wondering, so you're using the human to get these like energy optimal geodesics, right? But then you're mapping that to a space with a different number of degrees of freedom. So, is that actually, I guess, like guaranteed, or even should that be optimal in the 8 degrees of freedom? If you're like, even if it's optimal in 7 degrees of freedom, is there anything you can say about the optimality in like an extended space?
So it's indeed connected to the previous answer. So because we are mapping, at the end of the day, what we are doing is that we are mapping only the start and the end point of each segment, and then we reconstruct the geodesic between the segments in the space of interest.
Right.
And this geodesic is optimal.
Okay, makes sense. Thank you.
Okay, let me now go to the last part of the talk, where I would like to show you how geometry can be viewed as inductive bias that is introduced from human knowledge. So in robotics, we actually have a lot of taxonomies, and those taxonomies incorporate a lot of domain knowledge. So roboticists takes actually a lot of time to analyze motion and to really label them, analyze them, and shape them in the form of taxonomies. So examples are grasping taxonomies, we have quite some few, manipulation taxonomy or bimanual manipulation taxonomy, or here the whole body superposed taxonomy. Despite the highly relevant domain knowledge that we have in those taxonomy, they are actually barely used. So beyond the analysis application, we barely use those taxonomies. And we hypothesize that this is due to the lack of computational models that are bridging the gap between the taxonomies and their data. So let me explain that a little bit more. So when you have a robotics taxonomy, you have basically two parts of this taxonomy. The first one is a hierarchical structure. So this is typically a tree or a graph. This is a discrete structure. So here we have the example of the whole body support pose taxonomy. So each node of the graph is a support pose. That is a pose that is defined by a set of contacts of potentially different types. And when you go from one node to another, you're basically changing a single contact, right? So here, for instance, this is a 1 foot contact. Here you have a 1 foot, 1 hand contact, and you have a single change of contact between the two. This is why they are linked in the graph. Okay? So we have here this discrete hierarchical structure. Now with each of those nodes, we actually have data that are linked to each of the nodes. And in this case, the data are typically joint configurations, like joint angles, right, of the full configuration space. And those data are continuous, right? You have a continuous space of joint angles. On top of that, those data are often heterogeneous and high-dimensional. So you basically really have a gap between the discrete hierarchical structure and the continuous data that are associated with the node. So what we would like to do is to be able to learn a continuous representation of the data that actually capture the discrete hierarchical taxonomy structure, which is linked to this data. So in other words, we propose to learn a latent representation, and we would like this latent representation to be such that the data that belong to the same taxonomy node are grouped together, but that the distances between the different group of data belonging to a node are actually conserved in the latent space. That means that here we have a distance of 1 between the orange and the yellow node. We want to conserve this distance here. And here we have a distance, roughly speaking, of 2 between the orange and the pink node, and we also want this distance to be conserved. So here I have a graph made of 3 nodes, so yeah, I can embed that in the Euclidean space, it's completely fine. But now what happens if I'm considering the entire taxonomy is that the Euclidean space doesn't have enough volume to actually embed the entire tree. So you see in that example, for instance, here, you have 2 children that are very close to each other, but the common parent is very far. So those 2 children should actually be very far from each other and not very close. So basically, it doesn't scale in the Euclidean space. We just don't have enough volume. So what we can do instead is to consider a different geometric space, in that case the hyperbolic space, which is the set of points that have a norm smaller than 1. So everything that is inside that circle, basically. What is super cool with that space is that the distances grow exponentially when you move away from the origin. So to illustrate that, you can check here those birds. And you see that we have different blackbirds, and we see them smaller and smaller the further away we go from the origin. But actually, in the hyperbolic space, all of them have the same area. So the volume grows exponentially when you go away from the origin. And this is super cool because it's ideal to embed taxonomies. So you can embed trees exactly in those hyperbolic spaces. So it means that in that case, also when you have geodesics between typically here this pink and orange node, this geodesic almost makes you pass through the common parent of the tree. So you can really embed trees exactly there. So what we propose to do is a Gaussian process hyperbolic latent variable model, where we have latent embedding in a hyperbolic space, and then a Gaussian process mapping to our high-dimensional continuous observation. So here our hyperbolic space is also continuous. So at the end of the day, we have a Gaussian process mapping between our continuous hyperbolic space and our high-dimensional observation space. Because our latent space is hyperbolic, we modify the kernel of the Gaussian process such that it is a Riemannian kernel. So this is the same type of techniques that I showed at the beginning. We put a prior on the latent space, which is hyperbolic. So this is a wrapped hyperbolic Gaussian distribution. And then when we optimize the latent embeddings, as we usually do in GPLVM models, we actually use Riemannian optimization instead of classical optimization techniques. Now you can do that, but you don't have any guarantee that the embeddings are going to actually be organized according to the taxonomy. They will belong to to a hyperbolic space, but you don't have any taxonomy organization. So what we do is that we add an additional loss, which minimize the difference between the distances that we observe in the taxonomy and the distances between the different nodes in the hyperbolic space. And then we also add some back constraints, which allows us not only to map from the latent space to the observation, but also from the observation space onto the latent space. So let me show you what it gives here for the whole body proposed taxonomy. So this is the embedding that we obtain in two-dimensional hyperbolic space. So you see that here the embeddings are grouped and organized according to the taxonomy node. So you see that the different colors are grouped together. You have two groups of some of the colors, typically here one yellow and another yellow, because we separate the left and the right contact. So one of those yellow ones is for the right foot contact, as you can see here, and this one will be for the left foot contact. So this is why we have two clusters usually of each color. You can compare that if you don't add the stress loss, so this additional taxonomy prior somehow. You have the vanilla Gaussian process hyperbolic variable model, and you see that the nodes are not grouped according to taxonomy nodes. Now we can compare with Euclidean embeddings, and we actually have a look at the stress value, so the difference between the distances in the latent space and the distances in the taxonomy, and you see that the hyperbolic space reaches lower stress value, so better match the distances. Using the back constraints, we are able to encode unseen poses, so observations that we didn't see before, we encode them in the latent space, and they will be organized as well according to the taxonomy. Using the same principle, we can actually expand the taxonomy and add new categories, and they will fall at the right distance compared to the taxonomy that are already embedded. And finally, we can generate motion by simply following geodesics in our hyperbolic space that will respect the structure of the taxonomy. So you observe the right transition in the motion that are generated. And I think they look quite realistic, at least in my opinion. Now we actually compared the motion that we obtained with the motion that are obtained by a V-poser. So this is a state-of-the-art, it's a variational encoder, actually, which embeds a lot of prior on human motions. And this is actually trained on 1 million of data points. Our is trained on 100. So basically, simply by adding the structure of the taxonomy in the right geometry of the latent space, we are able to obtain similarly realistic motion as a model that is trained with 1 million of data. So another example with another taxonomy. So this is a grasping taxonomy by Stival et al. So where the grasps, for those of you who know the taxonomy by fakes and all, this is the same grasps, but they're organized in a tree which link, so that the grasps that are kinematically and from a muscular perspective close are close together in the tree. So here is the embedding that we obtain, again with our back constraints and additional stress loss. Again, you see that the embeddings are grouped and organized according to the taxonomy node. So you can see, for instance, here the yellow, which are the grasps here that are close together in the tree, are close together here, and they are very far, for instance, from those which are here in the other side of the hyperbolic space. Again, we can compare with Euclidean embedding, and we see that here the stress is arguably lower in the hyperbolic space than the Euclidean one. It's even more critical here simply because our taxonomy is a pure tree, while before we had a graph. And the hyperbolic space can exactly embed trees. Again, we are able to generate motion between different categories of taxonomy. Here what is interesting is that usually transition between grasps are actually hard to collect in humans. So we are here really generating transition between grasps that are absolutely not observed in our training data. So what I wanted to show you here is that by considering geometry that comes from human knowledge, we are able to have a taxonomy over latent embedding and to generate realistic human motion with only a few data. So just to conclude, what I wanted to show in that talk is that incorporating geometry as inductive bias in the form of a data structure allows us to have faster convergence, better accuracy, and lower solution variance in learning algorithm. When we consider geometry from physics, we are able to simply generate dynamic motion with energy minimizing trajectories that are specific for the robot at hand. And finally, by considering geometry that comes from human knowledge, we are able to have continuous representation of human-designed discrete taxonomy and to have realistic motion generation with only few data. So I hope that I managed to convince that geometry is a powerful and expressive form of inductive bias for robot learning in general. So here are the papers that are linked to the different part of the presentation. There is here an additional preprint to show good practices when we use Riemann geometry in robot learning. This is the link to the YouTube channel of our first tutorial, and again, we have the second edition at ICOL 2024, and we'll be happy to see all of you there. Thank you very much.
Okay, a couple of final questions. Anybody? Yep, one. I see you gentleman in the back.
Right, great talk. I have three questions. I'll ask two of them. So the first one is when in reinforcement learning, when we try to optimize the motion of humanoid characters, we see these super weird motions that seem physically implausible. I'm wondering if you are thinking about integrating some of these geometry inductive biases into the design of RL optimization algorithms.
Yes, I mean, that could definitely be one way. For now, what we are actually trying to do is to try to even improve our hyperbolic embeddings. For instance, we don't consider here constraints, which could typically be linked to dynamically feasible motion. So yeah, that kind of things. But then, based on that, probably we could actually incorporate in some way this notion of geometry and taxonomy into the reinforcement learning algorithm as, again, as inductive bias, I think. That would be a nice idea.
The other question is, in order to incorporate, so for the hyperbolic embeddings, you need to know the structure of the tree a priori, and then you figure out the embeddings after you know the structure.
Yes. Yes.
Is that always necessary? Is it possible to infer the tree structure while optimizing the embeddings?
So I'm not sure, then you will probably need to have additional costs that actually pushes you to infer a tree structure. The problem that arises if we don't put our additional loss where we know the taxonomy is that basically embeddings that belong to the same node, because you may have embeddings that belong to the same node, but kinematically they look a bit similar, and then you will have them mixed. So I guess maybe you could, but then you would need like some additional function that really pushes you to separate categories according to some other driver, I would say. Or you may learn the taxonomy and then learn your embedding.
Thank you.
Thank you.
So, with respect to the last, like the hyperbolic embedding, could you combine like the mass matrix metric and the hyperbolic metric so that you get more realistic motions when you're plotting those geodesics?
We're actually working on that.
Cool. Thanks.
Any more?
I might take an opportunity.
opportunity to test one. So this is fantastic stuff, actually, really, really interesting. In many of the cases, so for example, geometry for physics, we touched on it when we talked about data structures. We have a good understanding and knowledge of the manifolds that we know well, SO3, okay. And you can, of course, you can paste them together, which is used for humanoids. Do you have any thoughts as extrapolation? If you don't know the manifold structure, but you would love to say something about its simplicity, hopefully, like discover simplicity, I guess. You discover underlying Riemannian geometry that is not overly complex. Any thoughts on that? I'm thinking of like image data, for example, where we don't necessarily know what the underlying manifold structure is, but it's probably in there, and it's probably something, maybe in many cases, it's tractable. Maybe.
Yeah, typically for those cases, what people do is that they learn the Riemannian metrics, so typically by those variable models. For images, this is actually what people do. And then you obtain a Riemannian metric. The point is that usually you don't have a nice close contribution for exponential map, a logarithmic map, geodesics, and all that. So either you go and you solve a second order differential equation, ordinary differential equation, or you use approximations. Does it answer your question?
Yeah, no, it still works. It's great. Yeah, oh, very good. Okay, any other questions? All right, that was fantastic. Okay, so let's thank our speaker one more time. Now we have a little bit of time here, yes, so we can, if you'd like to catch up with Dr. Jaquier and maybe ask a few questions in person, we have a few moments or a few minutes afterwards to do that. So, all right, thanks again.
Thank you. Yeah.